Right. Well, the name is actually pronounced Casciani. I'm an Anglo-Welsh, Italian, East London, Cockney, mongrel. But there you are. As a bit of background, I originally served an apprenticeship in a shipyard on the River Thames. Back in the 1940s, I qualified as a naval architect, and after some years at sea and working in a shipyard drawing office, set out as a marine surveyor in about 1960. And I finally retired in 1975 when my wife died. I thought I've had enough of this and gave it up. But I still keep doing odd little bits, and it keeps me amused, if nothing else. There we are. Now, can we have the next slide, please, Mike? No, another slide. That's it. I've given you here a few of the available documents that you can read. Actually, if you go on to Google and type in the name of one of these bugs, you will literally get millions of documents, and most of them are concerned with the oil and coal mining industries, but you will get some that will give you some valuable information about ships and boats. Let me make it quite clear at the beginning, I am not a microbiologist. I'm a shipbuilder, ship surveyor, and so on. I do not know how these microbes work, nor do I know their biochemistry or their lifestyles. I have, however, seen many times the results of their depredations on ships, ocean-going, small craft of many types, and those confined to inland waterways, and that is what I intend to talk about. That and how the average marine surveyor walking around a ship or boat on blocks in a dry dock or on a slipway can spot the distinct type of corrosion, identify the probable culprit, and know how to deal with it. Now, ship and boat owners and marine surveyors will, of course, be very familiar with common ferrous and ferric rust in whatever form it takes. And all marine surveyors should not only be able to recognise the 5 different types of electrochemical corrosion or rust on site and understand the conditions that cause the problem, but also how to deal with those conditions in order to minimise the deleterious effects of the result on a vessel's structure. The literature on the subject of electrochemical and galvanic corrosion is likewise enormous. Biological attack, however, is not so widely known about, understood or recognised. But in the marine world, it generally takes one of 2 forms, called macrobiology and microbiology. Macrobiological attack is the well-known phenomena of mussels, barnacles, slimes, grasses, seaweeds and algae, etc., attaching to a ship's hull. These items do not usually cause serious harm to the metal, but they can and do slow the vessel down and increase her fuel consumption for a given speed. They are more or less satisfactorily dealt with by regularly slipping or docking, scrubbing the hull clean and coating her with a suitable anti-fouling paint and fitting the vessel with a properly designed cathodic protection scheme. However, there is a different type of corrosion which is also found on ship hulls, particularly those lying in waters such as canals or rivers containing decaying vegetable matter. Very few people seem to be aware of the problem or that it is caused by microbiological attack, or in other words, in my cynical world, metalworm. Now, microbiologically influence corrosion, MIC, Also known as microbial or biological corrosion, is the deterioration of metals as a result of the metabolic activity of microorganisms. There are about a dozen, possibly quite a lot more, bacteria known to cause these microbiologically influenced corrosion of carbon steels, stainless steels, aluminium alloys and copper alloys in waters with pH values ranging from 4 to 9 and temperatures of between -10 and +50 degrees C. The bacteria are found down mines and oil wells, under the polar ice caps, at the bottom of the oceans, around the so-called fumaroles, in harbour muds, canals and rivers. They're there everywhere, and they've been on the planet Earth a lot longer than we have. The phenomenon also costs the gas and oil and mining industries many dollars, and there are many articles on the subject, mainly referring to their experience, and the bacteria concerned are freely available on the internet. The problem, as far as ships are concerned, has been known for about 190 years. The iron bacterium called Gallionella ferruginea was first named by a man called Ehrenberg in 1836 and was mentioned, but not named, by Barnaby in his 1954 book, Basic Naval Architecture. The bacteria play an important part in oxidizing and fixing iron, but in order to get the energy out of that process, they must live in a relatively specific environment that contains reduced iron, the right amount of oxygen, and sufficient amounts of carbon, phosphorus, and nitrogen. I first came across these bacteria when I was an apprentice in the old Orchard Dock, one of the Blackwall shipyards, in the 1940s. In those days, we regularly dry docked the barges that attended the dredgers that maintained the shipping channels in the River Thames. Those barges were fitted with side buoyancy tanks and bottom doors, and the sloping inboard sides of the buoyancy tanks often had a very particular and distinct type of corrosion. We often had to replate them. When I was asked a Lloyd surveyor what it was, he simply said microbiological attack. And since I was only an apprentice, one of the lowest of the low in a shipyard, ignored me after that. That's life. In, I think, the early 1960s, there was a major court case in London which involved microbiological attack on seagoing ships. I do not remember the details, but do know that it was something of a cause célèbre and was discussed and mentioned over many issues of the Lloyd's List newspaper. The phenomenon was also brought to public attention when Dr. Robert Ballard found the wreck of the RMS Titanic and dubbed the detritus of the microbes attached to her side rusticles, because they look like icicles made of rust. They are actually ferrous and ferric hydroxide, not rust. Despite the name, they are not true rust and must not be confused with it. As a direct result of the attack of the microbes, which are reducing her iron at an estimated rate of 0.3 grams per square centimetre of area per year, it is estimated that within the next 100 years, I have seen other dates or so, of the steel remains of the Titanic will have completely disappeared and turned into a mountain of ferrous and ferric hydroxide at the bottom of the ocean, eventually to disappear in the abyssal mud. Here's a photograph of her bow. you can see those rusticles hanging from the side. What happens is that they eventually get too heavy and fall off, leaving a new surface for the bugs to attack. And that ship, as I said, will virtually disappear in 100 years. In 2010, scientists also isolated what they called a gram-negative heterotrophic aerobic non-endospore forming bacterial strain that they named Holomonas titanicae, a motile by Peritrichus flagella, that is, little things that waggle at the back of the bug. They designated its strain BH1T from a rustical sample. Excuse me a moment. I intend to die of a very rare disease, bloody Matisse stream. They picked up a rustical from the ship and analysed it and got that result. It's pertinent to know that when a sample of the steel from the wreck's double bottom was brought to the surface, it was found to contain over twice the amount of sulphur that the classification societies allow for class ships these days. For a ship to be classed, the sulphur content of the steel must be less than 0.03%, which is very low. The Titanic, it was 0.67%. The bacteria can be broadly classed as aerobic, i.e. those requiring oxygen to become active, or anaerobic, those not requiring oxygen, as the gas is toxic to the bacterium. Sulfur-reducing bacteria, or SAB, are anaerobic and are responsible for most incidents of accelerated corrosion, damage to ships and offshore steel structures. They are also responsible for much of the damage to the bottom plates of canal boats, a region where, in accordance with Henry's law, free oxygen is a relatively short supply. Iron and manganese oxidizing bacteria are aerobic and are frequently associated with accelerated pitting attacks on carbon steel plating and stainless steel at welds. MIC is caused by a specific genera of bacteria which feed on nutrients and other elements found in the water. Sea and canal waters are a primary source of sulfate-reducing bacteria, or SRB. The biological activities modify the local chemistry, acid-producing, and render it more corrosive to the metals. For example, iron-oxidizing bacteria can perforate a 5 millimeter thick AS316 stainless steel tank in just over a month. That's fast. I was also once told of a case where the bugs had eaten through a 12-inch, 300 millimeters thick piece of mild steel in a year. But sorry, I have no further information on it. It's amazing how bugs can work. It's a highly unpredictable process, and the marine surveyor should realise that under the influence of microorganisms, corrosion processes can happen in a matter of months compared to the years it would take for ordinary abiotic corrosion to reach serious proportions. Further, also due to its unpredictability, it is often difficult to include microbiological induced corrosion in risk analyses, and more often than not, its possibility is not even considered in the vessel's design stage. The impact can be enormous, and it's an estimated 20% of all corrosion damage is caused by microorganisms, leading to costs as high as 2.5% of a country's gross domestic product. That's a lot of money. There's also been a very large amount of data published on this subject in the civil engineering field over the last 20 years or so, and it's widely recognised that not only does MIC stimulate general pitting, crevice and stress corrosion, but that it is also capable of enhancing other related defects in steel, such as corrosion fatigue, hydrogen and nitrogen embrittlement, and cracking. Since the microorganisms are very widespread in nature, most natural and man-made environments are sufficiently contaminated to encourage bacterial activity to proceed to a greater or lesser extent. This type of corrosion is not a new form recently discovered, but it is only in the last 3 or 4 decades that its seriousness has been fully appreciated. The organisms are commonly found in ballast tanks, where the vessel has ballasted by taking on muddy river water, or lying in the mud of harbours or in the waters of canals, particularly those running through farmland, where surface water runoff often deposits chemical fertilisers into the canal. The author realised the severity of the problem some 40-odd years ago when employed as a superintendent engineer for a company running a number of general cargo Liberty ships, which often loaded ballast water for return trips from the West African coast. The ballast water was, from the nature of its loading from the rivers, often heavily polluted with vegetable matter and very muddy. On inspection of the ballast tanks at one of the classification surveys, very severe pitting of a clearly defined and characteristic type was frequently found under the mud deposits in the tanks, and a great deal of time and money was spent trying to find the cause of the problem. It was eventually identified as microbiological in origin when specimens of the corroded steel were sent for laboratory analysis. The per diem corrosion rates were as often as high as 800 milligrams per decameter squared, or if it's easier to understand, pits several centimeters in diameter, 8 to 10 millimeters deep, were often found in 18 millimeter thick shipbuilding quality mild steel plate in less than 2 years. That's fast, believe me. Such microbiologically assisted reactions are well known in the big ship field to be an important factor in marine corrosion, and there is again an extensive and increasing literature on the subject. This type of corrosion has been described for a number of different structures in the marine environment, for aluminium and copper alloys and stainless steels, as well as ordinary shipbuilding quality wrought iron and mild steel structures. The presence of the microorganisms has many complex and interrelated effects, and they can also generate environments favourable for the better known electrochemical processes to occur. They can, for example, destroy anti-corrosion additives in corrosion, depolarize cathodic processes, and produce severe changes in local oxygen percentages that lead to differential aeration and concentration cells. The microorganisms that contribute to corrosion are many and varied, and include aerobic bacteria, fungi, algae, diatoms, yeasts, and other organisms. They are able to colonize surfaces, producing biofilms up to 100 millimeters thick, and acquire the ability by genetic mutation to adapt easily to environmental changes. The systems are therefore dynamic and can and do change with time. Although it can be assumed that microbiological corrosion will ensue in any environment in which the microorganisms can survive, the extent of the activity of any specific species may be limited, and conditions favourable to one type may be quite inimical to another. The bacteria associated with the corrosion of metals are unicellular, possessing a thick, rigid cell wall divided by binary fission, and some have a flagellum to enable them to swim, a little waggly bit at the back. I prefer my English. And thus they are mobile. The organisms can be either autotrophic or heterotrophic, aerobic or anaerobic. Autotrophs obtain their energy from light or from the oxidation of inorganic materials and their carbon by assimilation. Heterographs are those bacteria that obtain both their energy and their carbon requirements from organic sources and assimilate carbon dioxide to only a limited extent. Anaerobic microbes do not require oxygen for their growth, whereas aerobic bacteria do. The unicellular bacteria have three basic shapes. They can be rod-like, curved, or spiralid and spherical. They vary considerably in size, typically a maximum size of 1 micromillimeter. In other words, you can't see the damn things. They're invisible to the naked eye and fall mainly into 4 types. Slime formers, grasses, seaweeds, etc., which form slimy and other coverings over steel surfaces, reducing oxygen transport and trapping particles of debris. Sulfur oxidizing bacteria, or SOB, which produce hydrogen sulfide from dissolved sulfates in anaerobic conditions. The bottom of the result is black. I have a picture to show you later on. Wet hydrogen sulfide is reported to corrode mild steel at rates that can exceed 2.5 millimeters per cm squared per year, but it doesn't corrode aluminium alloy to the same extent. Sulfur-reducing bacteria, or SOB, which produce tetrahydrated ferrous sulfate and the highly corrosive sulfuric acid. The bottom of the pit that results is silvery white, and again I can show you some photographs. Iron oxidizing bacteria, IOB, which oxidize soluble ferrous iron, produce an orange-brown powdery insoluble ferric or oxyferrous hydroxide. Horrible as the idea may be, you can actually eat the bloody stuff. It just goes straight through, but it doesn't taste very nice. I don't intend to discuss the slime formers, grasses or seaweeds, or for that matter barnacles and similar creatures, as they're very well known to all of you. Anybody involved in slipping or docking a ship will have seen them. This talk concentrates only on the microbes that attack the ferrous metal surface of the shell plating. The marine surveyor reading the literature will often come across the phrase gram staining. You don't need to know much about this, as it's a microbiologist's domain, but it is a laboratory method of identifying the different bugs. Gram staining, which is also called Gram's method, is a method of differentiating bacterial species into two large groups called gram-positive or gram-negative, and was invented by a man called Hans Christian Gram. Now there's a surprise. It differentiates bacteria by the chemical and physical properties of their cell walls by detecting a chemical which is present in the thick layer of gram-positive bacteria. A gram-positive results in a purple-blue colour, while a gram-negative results in a pink-red colour, which shows that the iron is acting as a detoxifier for the harmful sulfide, which enables a higher growth for the sulfate-reducing bacteria to grow. There are four groups mentioned, however, and the most important group associated with the corrosion of ferrous metals are those in whose metabolism sulfur and or its compounds plays an important part. Remember what I said about the sulfur in the Titanic steel. Pitting from microbiological sources has a high surface area depth ratio. The sides of the pits are stepped and the bottom of the pit is flat. Sulfur-reducing microbes leave the bottom of the pit coated with a soft black substance, easily cut with a penknife and giving off the characteristic bad egg smell of hydrogen sulfide. Sulfur oxidizing microbes leave the bottom of the pit covered with a bright silvery white coloured, very hard substance. Now, talking about the oxidizing bacteria, these oxidizing bacteria are from the genus Theobacillus and are usually referred to as SOBs and perform the oxidization of sulfur to sulfuric acid. The acids produced can cause deep pits to appear in the ground metal, though their involvement in the corrosion process is only slight compared to the sulfur reducers. The bacteria are autotrophic, acidophilic, short, non-sporulating rods, approximately 0.5 to 1.5 micrometers in size. They occur as single cells or in pairs and are mobile. The optimum temperature for growth is about 25 to 30 degrees C, but they die at temperatures above about 55 to 60. They are colourless, rod-shaped, gram-negative bacteria and have polar flagella. They possess an iron oxidase which allows them to metabolize metal ions such as ferrous iron. They are strictly aerobic bacteria, and all species are respiratory organisms and are obligate autotrophic organisms. You'll obviously need to have a dictionary at hand when you read this, meaning that they require inorganic molecules as an electron donor and inorganic carbon, such as carbon dioxide, as a source. They obtain their nutrients by oxidizing sulfur and iron with oxygen. Theobacillus microbes do not form spores. As I said, they are gram-negative. Their life cycle is typical of bacteria with reproduction by cell fission. The two main strains are Theobacillus theoporus and Theobacillus ferrooxidans. It's the later one, oxidans, which you will often find on boats in the canals. It affects the precipitation of ferric iron solids. The flat bottoms of the pits, which are usually about 1 millimeter deep, formed by their action are covered with this silvery white tetrahydrated ferrous sulfate, also known in its mineral form as rosinite, and a clear identifier for the Theobacillus group. Note also that the photographs below, the high surface area, can I look at the high surface area, a depth ratio of the pitting. You see the white silvery surface. That is typical bug attack Theobacillus ferrooxidans. When you see that, you know exactly what is happening to the steel. I'll tell you how to deal with it in a minute. Can we have the next one, please? Right. Here's another one. This is the one with the hydrogen sulfide in it. You can see the black colour that stands out quite clearly. When you see that, you know you've got serious trouble. If you scrape that with a penknife, you'll get the distinct smell of rotten eggs, which I'm sure all of you are familiar with. Let's move on to the next one, please. This one shows you the bug attack on a pipe. The pipe is a cooling water pipe from the main engine, and it's on the outside of a Dutch barge. And as you can see, that is also Theobacillus ferrooxidans. Those bugs will eventually eat through that pipe, with the result that you will get salt water in your cooling water, which will, shall we say, make a mess up of the engine, which is the polite way of putting it. Okay, next one, please. Here's another one. Again, that silvery white stuff. Notice also, if you look carefully at the white stuff, you will see that there are pits underneath it. That vessel was suffering from electrogalvanic corrosion before the bugs got their teeth into it. They've gone over the top. All right, let's go on to the next one. Now here's an interesting one, because the silvery white is the Theobacillus ferrooxidans, and you see the orange-brown rusticles, for want of a better word. They are Gallionella ferruginea, and those two bugs often work in cahoots together. I don't know why, I don't understand the chemistry, I've never studied it, but you often see them together. And that has got to the stage where it needs some serious attention. Okay, move on to the next one, please. I will deal with that one in a minute. Have you got that? Ah, right. Right, we'll use that. Okay, we've already done. Now the, okay, I'll leave that one up for you to look at, because I think that's the best one of the lot. It shows the two bugs very clearly, and that's well worth keeping. Talking about the sulfur reducing bacteria, they can create problems with metal structures when they're exposed to sulfate containing water. The interaction of the water and metal creates a layer of molecular hydrogen on the metal surface, and the sulfate reducing bacteria then oxidize the hydrogen while creating hydrogen sulfide, which contributes to the corrosion. The completion of the sulfur cycle, the type 2 bacteria of the desulfomaculum reducens Why they had to make them in such difficult Latin words, I don't know. I studied Latin for years and still can't pronounce the damn language. How the Romans got on, I don't know. And the desulfuricans, they can carry out the reduction of sulfate to hydrogen sulfide, which produce the black surface that I showed you earlier. Right, okay, we'll go on to this one. I haven't seen too many of this particular type of bug, the desulfurovibrio. It seems to be a bit rare within the number of ships that I have seen, but it is very common, particularly on ships that have been located in mud, laid ashore in mud anywhere. It's a gram-negative sulfate-reducing bacterium, and it's commonly found in aquatic environments with high levels of organic material and sulfate. The sulfate is reduced to sulfite, and the latter interacts with the ferrous iron to generate the black medium which you've seen. They are known, these bacteria are known as aerotolerant. They are straight and curved rods, are highly heat resistant, and have a free living fixer of atomic nitrogen. They can live in a lively partnership with the type 3 bug, which you can see there. The two types of bugs can work together again. Once the bacterium has started to produce sulfides, the local conditions then come favourable to growth, and that can result in a population explosion of the bugs, all producing highly corrosive sulfides. Any source of water which contains soluble or decayed organic material makes an ideal environment for these bacteria, and such water can have very high expectation of contamination with SRB. The usual nutrients available are phosphates, sulfates, and nitrates, all of which are free-flowing into rivers and canal systems near farmland. And they're a prime example of water, particularly if they're running through farmland, where all non-organic methods of fertilization and the use of chemical fertilizers may be expected. Marinas fed by rivers are another such example, and it's well known that harbour muds are highly contaminated with sulfides produced by these creatures. Right, that's that. We've already seen that one. I cannot give you details of the following thing, as the matter is sub judice. But I know of a case of a £500,000 steel yacht which lay in a mud berth after completion for some weeks. When the owner had her hauled from the water in Spain, the white bottom coat was covered in a black coat smelling strongly of hydrogen sulfide. The shipbuilder has refused point blank to accept a scientist's statement that the damage is due to microbial attack, but it's going to a high court, and we'll find out in due course what the high court thinks of it. Now, probably the most damaging one that you will see is the iron bacterium, or Gallionella ferruginea. This one, as I said, has been known since 1830 something. So it's not yesterday new boy on the block. It's been around for close on 200 years, known about. It lives in low oxygen conditions and has been found in a variety of different aquatic habitats. The bacterium obtains its energy from carbon dioxide fixation by oxidizing ferrous ions in solution to ferric oxide ions, with the consequent precipitation of ferric and on normal shipbuilding quality mild steel, manganic hydroxides in the form of clearly visible orange-brown tubercles on the underwater shell of the vessel, as you can see in the photograph. This type of attack is often found on the lower sides and undersides of the bottom plates of narrowboats and, for example, Dutch barges used as houseboats. The iron bacteria are rather like living porous concrete and start with a thread-like polymer structure and then crystallize iron, calcium, and a tiny bit of aluminium. The outer surface of the rusticle is heavy with iron, and that protects the resident colonies of bacteria. The outer skin grows harder and darker with age, which fact helps the marine surveyor to spot the newer growth. The young rusticle absorbs more and more iron from the parent source, which is consumed into the communal structure. If they stop consuming, they die, but if they carry on consuming, the ends of the rusticle becomes too heavy and breaks off, as will happen on the Titanic. And the microbes inside then die. The old ones fall off, leaving a clean gap upon which a new colony can start. The rusticles left behind by the Gallionella microbes form a brown powder with a hard but brittle crust. They're a mixture of ferrous and ferric hydroxides, which are insoluble in water and are known as ferrous or ferric hydrate or iron hydroxide. The steel underneath often has a black lustrous characteristic of ferroso-ferric oxide, and its full identification is needed for legal purposes. Then a full lab report is necessary. Can we show that one, please? Right. A common method of identifying the particular bacterium found causing hull corrosion, sufficient for most marine surveying, is given in this table. And I'll leave that for you to look at for a while. Oh dear, oh Lord. The question is, once you've discovered it, once you've identified it, what do you do about it? The discovery by a marine surveyor of such microbiological corrosion is often very difficult and requires some experience because it's not always readily visible. It is usually found under muddy and slimy surfaces, sometimes even behind paint coatings, and a very careful visual inspection is necessary to locate it, and the marine surveyor to know exactly what he is looking for. It's not amenable to discovery by non-destructive testing, such as ultrasonic thickness testing measurements, eddy current testing, or the magnetic methods familiar to most marine surveyors. Electrochemical methods of identification using a sulfur test can be used under controlled conditions, but it's difficult and takes a long time and rather unselective. The common practice of non-blacking the underside of bottom plates of narrowboats in the canals, for example, can only encourage this form of corrosion, and indeed I have often found it in such places. If MIC is discovered, it used to be practice To thoroughly clean the hull with a high pressure fresh water, allow the hull to dry off, and then coat it with a good quality biocide, sodium hypochlorite or common bleach. Wash off again, afterwards carefully recoat with a compatible paint. However, because of environmental concern, that has been considered better to use a 70% percentage of isopropyl alcohol. That's the spirit stuff that when you go into a hospital, you're asked to wash your hands with before you go into the ward. That spray, rather than bleach, then kills the microbes in little more than seconds and has no ill effect on the environment as it evaporates very quickly. 2 coatings should be used with a high pressure water wash between. Beware, the chemical is highly flammable and should not be used in a confined space. Again, mouth and eye protection should be used during the operation. Within my experience, the best paint to apply is a good tar epoxy and at least 4 coats with a minimum total thickness of 250 μ. Microbiological corrosion, microbial or biological corrosion, call it what you will, can be controlled and even prevented through a number of methods. One is the obviously properly applied suitable coatings. The other one is a correctly designed, not guessed, cathodic protection scheme. Too often they are just guessed. How many anides do I need, surveyor? 4 will do along there. Oh yeah. You can put too many anodes on, you can put too few. You can also put the wrong type on and the wrong area. Right, they should be properly electrically connected to the material that's being protected and suitable for the salinity of the water in which the vessel lies. You should be aware also that probably due to the movement of ions from the anode to the metal plate, the area around an anode, about 1 meter in diameter, is usually free of microbiological attack. I suspect that this is due to the microbes not liking the electric current, though I can't be sure of that, or I have any proof of it. Anodes generally reasonably protect an area of about 2.5 to 3 meters radius. They should not, of course, be painted, though it's amazing even these days you see painted anodes. They last an awful long time if they are. A good practice when painting the boat is to clean the anodes all over right back to bright metal, then coat them with soft soap or Vaseline before applying the paint to the hull. Any paint accidentally applied to the anode surface will then wash off and with the soap when the boat is floated, taking the unwanted paint with it. Experience has shown that in the absence of SRBs, adequate protection of mild steel is often achieved when there are sufficient anodes such that the electric potential is depressed by minus 0.85 volts when compared with a silver chloride anode. If the microbiological activity is high or the risk is known to be present, however, the potential may be reduced to at least -1 volt. That's it for you, folk. If you've got any questions, I'll do my best to try and answer them.